In this module, we encountered this example that I'm using here, where a student provided data from trying to determine how long of an air column was needed to produce resonance with different frequencies of tuning fork. So I have that same data here. I've added a little bit that we'll talk about soon, but first I want to talk about this graph, the resonant lengths of a closed air column, where we have frequency of sound on the x-axis. You can see I have a trend line chosen for it. But when we were doing the examples before, the trend line, we didn't exactly know which one to choose at the time, because we were just showing how to do it, not why to do it exactly. So in Excel, when I click on the trend line, then I get a bunch of different options. You should see that in other spreadsheet programs too, in whatever menu settings they use. So if I'm going through the different options they have, our default choice always tends to be linear. But mentioned before earlier in the module, that misses the error bars on this particular data point here. Now that might not be a problem. Maybe this is an outlier, but maybe not. And we're going to talk about that as well. So if I look at the other options, just out of curiosity, we can see how well they fit the data in terms of the error bars. But how to choose exactly which one we should use? Well, one way is to look at this r-squared value, which I've put on the graph. So you can display the equation on the chart, you can also display the r-squared value on the chart. So with the r-squared value, what that's telling us is how close the line that's been drawn comes to each of the data points. So it's doing an averaging of the distance between the line and the data points. So the closer it is to 1, the better fit it is for your data. It doesn't tell us anything about the quality of our data points themselves, just how close the line that Excel is drawing is to the data points. If we go through the options again and we look at those values, the polynomial trend actually has the best r-squared value. So why then would I have a power as my fit? When I started out, I had that already chosen, so you could probably assume that's the one that I like the best. Well, because the r-squared value can give us a hint, but we still have to go back to the physical situation and decide what makes sense for us. So if it's on a polynomial, if we look at the equation it gives us, if I put x equals 0, I'm going to get 631.99 or 632 for my y value, which is the length of the column that's going to produce resonance. Well, if I have a frequency of 0, which is the x value, it doesn't make sense to have a value like that. So why not? Because the first harmonic occurs at a quarter of the wavelength in a closed air column. Wavelength is inversely related to frequency of sound. So if I have a 0 frequency of sound, I should have an infinitely long wavelength. If I take a quarter value of the infinite wavelength, it's still infinity. So I shouldn't have any value here. 632 may seem like a large value compared to some of these other numbers, but it certainly is nothing compared to infinity. But if I look at the power, then now if you put 0 in for the x, since this is a negative exponent, it's in the denominator, that's going to give you a vertical asymptote at the y-axis. So that fits the physical situation that we have. So it has the second best r-squared value, but it meets the physical requirements of the situation. So it's the one we should be going for. Okay. So that's how we choose which trend line is the best trend line. But if it's not a linear trend line, then we might have difficulty analyzing it mathematically after that. So we'll go through another couple of things you can do in this video. Okay, one thing we can do is if this is our trend line that we're going to report in our conclusion, that this is the relationship of the data, then we might think about what these numbers mean. If you look at the exponent, it's a little bit small, but it says negative 0.984. Now the theory says that the length of the air column should be inversely related to the frequency of the sound. So that should be -1 according to theory. So we can do a percent difference calculation between it. That could be one way we can take a look at the results. Another way is that this number in front, the 76,834, that should be related to the speed of sound and also related to the temperature in the room, because the speed of sound is dependent on the temperature in the room. And I'll show you, well, you can see the equations if you look ahead on the right-hand side, but through what I show in a few minutes, you can see how you would actually calculate the speed of sound from this. But if you do, I just put a note in here that it'll give you negative 39 degrees Celsius. So obviously the lab wasn't that cold when we were doing the experiment, right? So that's going to be some indication of something going on with our data perhaps. But with a nonlinear trend line at the secondary school or high school level, it's not really too much we'll do with it mathematically. So instead, what we can do is we can try to make a linear trend. So we can either linearize the data just by using mathematical procedure, but we can also use our knowledge of physics. So if we instead do the length of air column against wavelength, we would expect to get a linear trend. So that again comes from the theory, but to do that we need to have values for the wavelength. So what I've done here is I've assumed a temperature of 25 degrees Celsius, which is standard room temperature. This student didn't record the room temperature, so it's just a guess, but I just put it in there to show as an illustration. So if I use that value, I can calculate that the speed of sound should be about 346 meters per second. So if I use that, then I can get the wavelength. And once I've got the wavelength, I can apply it against the length of air column, and we can see how closely it matches. Okay. Now you can take this gradient that we have here, and you could compare that to what it should be by theory, which would be 0.25, because it's the length of column is supposed to be a quarter of the wavelength. So you could make that comparison. You can look at the y-intercept and see if you can find meaning there. Now that it's a linear graph, we could do our other communication processing, where we could get a max fit line and a min fit line, and we could get an uncertainty on the gradient, and we could use that as well to talk about what this number here might mean. And there's still a bit more we can do with analyzing the data. So that's another graphical analysis we can do. But there's a bit more we can do with just raw calculation. So I mentioned before that we can calculate the room temperature. So what I've done here is I just made this little table with the frequency of the tuning fork just copied directly from the other graph. The wavelength from the first harmonic is just the average length, so the 285 here for the first one, times 4, because the theory predicts that we should, in a closed air column, we should achieve resonance for the first harmonic at a quarter of the wavelength. So to get the wavelength, we just have to multiply that length by 4. So I did that for each of the data points. Now I can calculate the speed of sound, and here's where you can do that with the formula. So the formula for the speed of sound is the frequency times the wavelength. So now that we have a value for the wavelength, we can multiply it by the frequency and get a speed of sound value. Now to get the room temperature, we can then use this other formula that comes to us from the literature, that the speed of sound is 331 at 0 degrees Celsius, and for every degree more in Celsius, you times by 0.6 and add that on. So if you're at 25 degrees Celsius, like I did before, you would go 0.6 times 25, add that onto the 331, and that's how fast speed of sound should be. So that gives you 346 is what I used in the other table. But here we're trying to solve for the temperature itself. So you rearrange the equation, take your speed that you've got, so 328, subtract the 331, and then divide by 0.6. And that's giving me -5. So the room temperature certainly wasn't -5. Like I said, the student didn't record what the room temperature was, but it certainly wasn't -5. 17 seems more likely, probably still a bit low. 23, 25, that's more likely to be what it was. -13, certainly not. 22 looks okay. 14, pretty low. So by using the data and some theory to generate numbers like these, we can assess the quality of our data in terms that we can understand a lot more easily. The room temperature is something we can all identify with, and if we want to, even though we've managed to get trend lines that will work with the error bar uncertainties and that make physical sense in terms of the 1 over x trend here, well, we can still choose not to use these data points because they're generating temperatures that are just unreasonable. The 14 and the 17, you might have a difficult argument taking those out because they're not quite so unreasonable, but the -13 and -5, we can remove those data points. So if you want to do even further analysis on this, you can take those out and you can refit. You can try and get a different formula here for this trend line, and I would imagine, I haven't done it myself yet, but I can leave that to you, to this coefficient will probably generate a temperature that's more likely to be true than -39. And we might get a trend that's closer to -1, but this is already quite close, so that the trend isn't too bad in that sense. So this video was meant to show you some ways that we can go ahead and try to interpret the data. When you're done interpreting the data, you come up with a conclusion that you're willing to state. And all of this work you've done in interpretation becomes your justification for it. So in a lab report, you would be reporting your conclusion, which has to tie back into your research question, and you would be presenting this analysis you've done, this interpretation that you've done, as justification for why you believe that conclusion is likely to be true. How likely it is to be true, you're going to use your uncertainty analysis to back up how likely it is to be true. There'll be an exercise to follow where you're taking another student-generated graph and trying to come up with your own ways to interpret the data.